about application of cold spray within additive manufacturing. Thanks so much for that, Tony. Ladies and gentlemen, nice to be here. Nice to talk to you about a slightly different additive technology than maybe some of you are used to. So this might be new to you, but we'll go on and we'll see. Okay, I'll be as loud as I can. Better? Excellent. So my name is Dr. Barry Aldwell from Trinity College Dublin. I'm a postdoctoral research fellow working in a technology called cold spray, which is usually used as a coating technology, but we're using it for more of an additive manufacturing kind of approach. So just a bit about Trinity College Dublin, founded in 1592, nearly 3,000 staff. Now those numbers are a bit old, but nearly 3,000 staff. Nearly 800 of those are academic, and around 600-ish are research staff, such as myself. Nearly 17,000 students, including about 4,000 postgraduate. These numbers are slightly old, but fairly representative. Over 100,000 alumni throughout the world. And of course, I have to mention rankings. We're always told rankings not mentioned until we drop in the rankings, and then the rankings matter all over again. We are first in Ireland with both rankings, but trying to get better. So I'm from the Department of Mechanical and Manufacturing Engineering. In the department we have 9 research groups, and then these groups just do research. You know, obviously the teaching side is a big element of it, but these are our research groups. I'm from the Manufacturing Technology and Systems Research Group. If you have any interest in any other research groups there, you know, give me a shout. I'll put you in contact with someone who might be able to talk to you. But I'm talking about some of our work in the Manufacturing Technologies and Systems Group. So in the Manufacturing Technology and Systems Research Group, some of our current research areas, obviously manufacturing processes are a big part of what we do. So we're cold spray for additive manufacturing, which is what I'm going to talk about today. We also do a lot of work in micromachining of biocompatible polymers, some machining of cobalt chrome, and virtual welding as well. And as part of that work, process monitoring is a huge element in a lot of what we do, so there's also some dedicated process monitoring research happening around surface acoustic wave sensors, and also some work on energy use for compressed air in industrial settings. So, cold spray in Trinity College Dublin. We have a dedicated cold spray lab. It is the only cold spray facility in Ireland, capable of spraying at pressures up to 30 bar and gas temperatures of over 500 degrees Celsius with a variety of materials, and full process monitoring capability built in, pressures, temperatures, flow rates, and powder feed rates. So when we're doing experiments, we record all that. If it works, we know what works. If it doesn't work, we know why it didn't work. So I'll just tell you a bit about the cold spray process. It is classified as a thermal spray process, even though there isn't a thermal element to it, or not a massive thermal element to it. It was discovered, or invented, depending on your perspective, in the 1980s in the Soviet Union. Essentially, in the process, powder is accelerated to supersonic velocities in a Dirichlet nozzle. So a nozzle very similar in concept, not an exact design, but very similar in concept to a rocket engine, converging, diverging profile, accelerates powder up to these supersonic speeds using a carrier gas such as nitrogen or helium. Nitrogen being a lot cheaper, helium being a lot faster. And the coatings themselves are formed by plastic deformation of the individual particles, also which are referred to as splats. So here in the bottom right, we have a picture of a single, I believe it's copper onto copper particle. And that's what happens. So that would have started as a spherical particle and accelerated up to very high speeds and formed a bond with that surface. One of the key features of the process is that we need a gas supply here, which can be quite substantial at times depending on exactly what you're doing. So I'll just give you a quick video demonstration of the process in action. So hopefully this will play automatically. Yeah, there we go. So my project is funded by the European Space Agency, that's why we do this demo. So this is in live action. We are coating aluminium onto copper. So you can see here is the nozzle through which the particles are being excited. And the sheet of copper is mounted on a XY CNC stage to actually make the motion to make this happen. So this individual track, if you were to measure the thickness, you're talking about 1.5 to 2 millimeters of thickness. If you were to measure it by putting through it. And as you can see here, the deposition rate is actually quite high, particularly when compared to a lot of other additive techniques. You can put down a lot of material very, very quickly. You can put down hundreds of grams per minute if you get your parameters right and you get everything working very, very well. So some of the advantages of cold spray, some of the reasons why you might use this over other approaches, other technologies. You can join dissimilar materials. So an example of this is shown here, where we have some copper coated onto an aluminium tube and quite a thick deposit. And also shown here, this is one of the ones that we're most proud of, aluminium deposited onto PEEK. So that's aluminium deposited onto a sheet of polymer. The aluminium is electrically conductive, and that is a very thick layer. Again, that's about 1.5 to 2 millimeters thick, deposited onto a polymer. Here we have another example of the copper onto aluminium, and talking about creation of constant materials. Bottom right here, not necessarily all that clear, but that is a diamond particle embedded within a copper nickel matrix. And we have shown in some of our results, in some of our tests, that you can get a diamond fraction in the vicinity of 45 to 50% of diamond by volume in a coating, which I actually don't think is possible or easily done with any other technique or any other approach. You can get very low porosities, very high densities if you get everything working right. And the key thing about cold spray is there is no phase change. Whatever you put in, you will get that in your coating. There's no melting, no recrystallization. So, cold spray for additive manufacturing. What I've shown you so far is very much coating based, or towards putting a coating. So cold spray is often used for hard facing or for putting a very thin layer of something onto a substrate. But why not use it for additive manufacturing? There's absolutely no theoretical limit on how thick you can make that deposit. No limit whatsoever in the theoretical way. There's no requirement for post-spray processing, heat treatment, etc. You can do heat treatment processes, you can improve various properties, but you don't have to do it. The coating is generally very machinable, very good machinability, very easy to do finishing process on it, polishing. So there's very large potential here for near net shape manufacturing, where you use cold spray to deposit a very dense layer of material selectively, then you machine that down afterwards to make what you're looking for. And cold spray is currently used by the US military and the Royal Australian Navy for repair applications, and there are also a lot of other interesting applications, such as putting down a layer of cold spray material and then friction stir welding onto that, or some nanocrystalline microstructure applications I'll show you in a minute. So, on the repair application side, this is a slide taken directly from a US Army Research laboratory presentation on cold spray, and you have 4 application areas here, all military, 4 application areas, Seahawk, 2 helicopters, B-1 bomber, and an armoured fighting vehicle, all of which they have fielded in the sort of 2008-2009 kind of range, fielded repair using cold spray. So this could be, an example is a gearbox housing for one of those helicopters would cost you over $100,000, and it's made out of magnesium. If it wears, if you get wear on the inside, unless you can repair that, you have to throw it away and you have to get another 6-figure gearbox housing out. Made of magnesium, can't really weld onto it, doesn't generally end well if you try that. Cold spray aluminium onto it, grind down to get back to the original geometry, it's back in service, it's back in action. If you're on an aircraft carrier, you're not flying out and flying in the gearbox housing, you're repairing it on site. And that's a huge, huge thing, and that's why they're putting a lot of money into it and a lot of effort into it. On the nanocrystalline microstructure side of things, this actually really impressed me when I saw it. So this is from a paper by Hall et al., where they took nanocrystalline powder, ball milled it to make the grain structure even finer, sprayed it, create a substrate, and then machine that, or to create a billet of material I should say, and then machine that billet to create mesoscale mechanical components such as these gear teeth here. You might not be able to see this scale bar, that's a 200 micron scale bar. So you're looking at gears with teeth of maybe 200 microns height. If you were to make these using conventional casting techniques, you run into a lot of issues depending on where your grain boundaries are, your dislocations are. They can and will fail, so you can't really control it. You use these nanocrystalline microstructured materials, you can make one of those that is going to last a very, very long time. And this is only really possible with cold spray. It's very difficult to do with these conventional casting techniques. So, the barriers facing in additive manufacturing, because it was easy to use, everyone would be using it. What are the issues? First issue, and this is a cold spray issue, is the gas requirements. You usually need an awful lot of gas at fairly high pressures and fairly high flow rates. So you can't just put one of these around the corner in your office. You need to have a purpose-built facility, you need high-pressure lines in, you need a way of getting that gas in. And it can be quite expensive depending on what gas you're using and what kind of amounts you're using. The second issue I have highlighted here, usually you have to have a very good idea of your process parameters. So you need to know what kind of deposition you're going to get. However, that's not just a cold spray issue, that's an additive manufacturing issue in general. You need to have a good understanding of what your deposition you're going to get to actually be able to know what you're making. And then the third one is definitely an additive manufacturing in general issue. You need to have, if you want to be able to do proper near net shape manufacturing, where you do additive and subtractive together, you're going to have a CAM package that does both together. And as far as I'm aware, there's not really a huge amount out there that does both at the same time. And you are also going to have to do some kind of metrology before you do any kind of subtractive operations. After you've built up the material, you have to check what's there and then machine it away. You need built-in metrology. So if you want to have a single machine that does both, you're going to have metrology automated built into that machine. So in summary, cold spray is an emerging technology in the additive sphere anyway. Fairly well known for coatings, but emerging for additive techniques. It does have some advantage over other technologies, and there's also great opportunities there for this near net shape manufacturing approach and combined additive subtractive together. So thank you very much for listening. I would thank the rest of the cold spray team in Trinity, including Dr. Rockley Poy, who's principal investigator in the research group. And if you have any questions, feel free to ask now or have a look at our website, which I will say at the bottom. Thank you very much.